This is lesson 4.6 titled Counting. We're going to discuss permutations and combinations, which are a common form learned in mathematics, okay? Now, first off, we need to understand what's called the counting principle, okay? And the fundamental counting rule states that you have m times n number of ways that two events can occur, okay? So here we have m times n. This is the number of ways two events can occur. For example, you have two character code. The first one is a letter, and then the second one is a number. Well, if we look at that and we think about it, how many different letters can you possibly have? Well, you can have 26, right? So the first number m would be 26. And then you have to ask, how many different numbers can we have? Well, there are 10 different numbers, 0 through 9, right? And so we would have 10. When you multiply those out, you get 260. So there are 260 different ways that you can have a two-character code where the first one's a letter and the second one is a number, okay? So that's the counting rule. Now, the reason why I showed you the counting rule first is because that's hopefully going to help us understand a little bit better about permutations. Now, permutations are this, okay? Permutations are the where the items are arranged in which different sequences of the same items are counted separately. So, for example, if you have ABC, you can rearrange ABC to be ACB, BAC, BCA, CAB, and CBA, okay? And so that's what a permutation is. It's just rearrange. How many different ways can you rearrange those three letters? Now, the important thing about permutations that you have to understand is permutations deals with order. So you use permutation when order matters. An example of that is a race. If you have a race and you want to know how many different ways 10 runners could come in first, second, and third. Now, because only one person can come in first, and another one has to come in second, and then another one in third, order matters. And so we would use permutations in that case, okay? So when order matters, we use permutations. Now, let's look at these examples I have on the board. The first example has A, B, C, D, E. They're all different letters, okay? Whenever we have all different items, then our rule for solving that is the one that you see written there. Here's our annotation, okay? N stands for the complete number of whatever amount is inside of however many you're looking at, okay? R is the part. P just stands for the permutation. So we're going to take the total number and do this symbol next to it. And then we're going to subtract these on the bottom and do that same symbol. Now that symbol is called a factorial. What a factorial is a factorial tells you to take whatever number is in front of it and multiply it by every number beneath it. So here's my quick example. 3 factorial means 3 times 2 times 1. Now guys, I rarely ever put the times 1 because times 1 doesn't really do anything to change a problem, right? If you do 5 times 1, you still end up with 5. So usually I would only write 3 times 2, even though you need to technically write 3 times 1, because factorial tells you to multiply it by every number beneath it. Now, looking at the first example, A, B, C, D, E, we have those letters, and we want to know how many groups of 3 can you get. Okay, so there are 5 letters here. So that's my N. That's the complete number of letters, N. So when I set this up, I have my P, 5 is my N, and I want to know how many different groups of 3. So 3 is my R. Now I'm going to plug that into the actual formula. This just tells me how to set up the formula. So on top, we have 5 factorial, because that's my N. On the bottom, we have 5 minus 3 factorial. Now 5 minus 3 is 2, right? So this is 5 factorial over 2 factorial. Now I'm going to go the long route with showing you this, and I think I'm going to erase this example even though I have it up there just because it's in the way, and I'll show you that part here in just a minute. Now, what I need to do here is 5 factorial means 5 times 4 times 3 times 2 times 1, I don't really put times 1 though, over 2 factorial, which is 2 times 1. Now what I can do here, guys, is I can reduce any number up above by the bottom number. So 2 can reduce 2 down to 1, right? When I multiply this out, this is 20 times 3, which is 60. So there are 60 different ways that you can rearrange those 5 letters into groups of 3, okay? Alright, so that's how that works. Now note that this is without replacement. None of those were replaced back into the probability of this permutation. Okay? Now, let's take the second example I had. I'm going to give you a new formula. Sometimes some items end up being identical or repeated items. So the numbers I had are, let me write the rule, it's going to be n factorial over n1 factorial, n2 factorial, and on till the last number factorial. And I'm going to explain that here in just a minute. So I had 4 A's, 2 B's, 2 C's, a D, and an E. Now, here's how this is going to work. Altogether, there are 10 letters here. So that's my N. So we have 10 factorial on top. Now I'm going to, the bottom factorials, these N's represent how many times each of these letters occur. So this is 4 A's, so that would be a 4 factorial. There are 2 B's, so that's a 2 factorial. There are 2 C's, so that's a 2 factorial. There's 1 D and 1 E, those would be 1 factorials. 1 factorial is 1, so again, I'm not going to write those. They're not necessary. Now in solving this out, you can do this in your calculator, by the way, so don't think you have to do it longhand. But here's a trick, guys. First off, the largest number on the bottom is 4. That means 10, since it carries down a factorial, and 4 was a factorial, the 4, 3, 2, and 1 would all cancel each other out, top and bottom. So I only have to carry 10 down to 5. 10 times 9 times 8 times 7 times 6 times 5. Because 4, 3, 2, and 1 would cancel out with this 4, 3, 2, and 1, okay? Over, now this is 2 factorial, so 2 times 1. And this is 2 factorial, so 2 times 1. And I don't put the times 1 because it doesn't do anything. Now I'm going to reduce in a couple ways here. I can reduce by 2 the 10 down to 5. I can reduce the 8 down to 4. I could have done this any other way I wanted to. Both those are gone on the bottom, so all I have to do is multiply 5 times 9 times 4 times 7 times 6 times 5. And the answer that you should get if you did that is 37,800 when you plug that into your calculator. Now guys, if you're not comfortable doing that with your calculator, then do it the long way. Put 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all in parentheses. Hit the divide button. Then do in parentheses on the bottom, or don't do it in parentheses, just do 1 parenthesis at the start. Do 4 times 3 times 2 times 1, and then do 2 times 1, and then do 2 times 1 again. Close the parentheses so all those numbers on the bottom are under 1 parenthesis. Hit enter and you'll end up with 37,800, okay? Hopefully that makes sense what I'm explaining to you. I can't really show you the calculator too well. Okay. Let me give you another example of a permutation. Another example or two. Okay. In how many different ways can 20 horses in a race come in first and second place? So this is 20 horses, first and second place. Order matters because we're talking about places. And so when I set up my permutation, since there are 20 horses, that's my total amount. And I want to know how many different arrangements of 2 horses I can get for first and second place. So setting that up, that's 20 factorial over 20 minus 2 is 18 factorial. Now guys, this is really easy because this goes 20 down, right? And this goes 18 down. So I only have to carry 20 down to 19 because 18 and down will all cancel out with each other. I'll give you a better example of that in just a minute. This will be 20 times 19. That's all that is. And the answer, all over 1, because 18 cancels down. 20 times 19, that is 380. So there are 380 different ways that you can get first and second place in a horse race with 20 horses. Now, let me try and explain to you this whole canceling out thing, okay? Let's say I have, let's go with easy numbers. 5 factorial over 3 factorial. Well, on the top, this would be 5 times 4 times 3 times 2 times 1. And on the bottom, this would be 3 times 2 times 1. Well, these can cancel each other out, these can cancel each other out, those can cancel each other out. I'm left with 5 times 4. Does that make sense what I'm trying to explain to you? So on the top here, where it was 20 over 18, I only have to carry 20 down to 19 because 18 and below would cancel out with each other. Okay, so there's your permutations. One more example. This is with identical items, so this is going to the second formula that I showed you with the n factorial over n1 factorial, n2 factorial, that one. A survey has 10 questions. 2 questions are the same and another 3 are identical. What that's saying is this, guys, that there are 2 questions where we have the same answer, so 5 and 5, and there's another 2 answers where there's 3 of them that are identical, so 7, 7, 7, okay? This is out of 10 questions. Now they often do this in surveys, guys, where they'll ask the same question several times throughout just to see if people are really answering it truthfully, okay? So, here's how this works then. We have a total number of 10, so that goes on top, 10 factorial. There were 2 identical ones to begin with, so that's 2 factorial. And then we had 3 identical ones, so that one was 3 factorial. So 10 factorial over 2 factorial times 3 factorial. The 2 bottom ones are multiplying, by the way. So when I go and solve this, I only have to carry 10 down to 4 because 3 and below would cancel out. So I'm going to do that. 10 times 9 times 8 times 7 times 6 times 5 times 4. 3, 2, and 1 would cancel out with that 3, 2, and 1. All over 2 factorial, which is 2 times 1. I don't write the 1. The 2 can cancel out anything I want it to. Well, let's cancel the 4 down to 2. We'll reduce it. We're reducing it down to 2. So that all I have to do is 10 times 9 times 8 times 7 times 6 times 5 times 2. And that answer gives me 302,400 different arrangements where you can have 10 questions with 2 repeated and 3 repeated. Okay? Alright, finally, combinations. Let me give you the formula for combinations. Recognize n and r. N factorial over, we have n minus r factorial. This is identical to permutation. Here's the one difference. You're also multiplying by r factorial on the bottom. So this throws in an additional number on the bottom that you're multiplying, and r factorial, okay? So combinations is the number of different number of different combinations when order does not matter, okay? Order does not matter in this case. And again, this is without replacement, so none of the numbers being used are going to be thrown back into the mix. If we have A, B, C, D, and E like we did before, we want 3, and we want to know how many different ways 3 can be selected, okay? Now, we're not saying any kind of order has to be important here. So, for A, B, C, D, and E, we have 5 letters. So for my combination, there's 5. And I want arrangements of 3. So when I set this up, this is 5 factorial over this 5 minus 3, n and r, 5 minus 3. So 5 minus 3 is 2 factorial. And then r factorial, that's just the 3, so 3 factorial. In solving this, I don't need to carry 5 down past 3 because it will cancel out. So that would be 5 times 4. On the bottom, this is 2 times 1, so I'll just consider it 2. 2 reduces 4 down to 2. 5 times 2 is 10. There are 10 different combinations of 3 that you can get out of A, B, C, D, and E. Now, you'll remember when we did permutations for that same thing where order mattered, we wanted groups of 3 where order mattered. We had 60 different arrangements. What's the difference in this calculation? Why is combination so much lower than permutations? Because we throw on there an extra division of R factorial, okay? Which is quite a difference. All right, so here's another example. Pennsylvania Lotto requires you to choose 6 numbers, 1 to 49. So 1 to 49, you have to choose 6 numbers. The winning number can be drawn in any order, which means order doesn't matter, okay? So find the probability of winning if one ticket is purchased. So we have to choose 1 to 49. That means the total numbers we have to choose from are 49 numbers. And we choose 6 of those numbers. Since we're only doing 1 ticket, we're only getting 6 numbers. Well, this is 49 factorial, my n, over 49 minus 6 is 43 factorial, and then 6 factorial. I don't need to carry 49 down past 43, so that'd be 49 times 48 times 47 times 46 times 45 times 44 over 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Alright, I can reduce each of these numbers, or you can just plug this into your calculator, put that into parentheses, hit the divide sign, put that into parentheses. These are all times, right? And you can solve that. Anyway, the answer you should get when you solve it is 13,983,816. Now guys, that's how many different combinations of numbers you can do of 6 numbers out of 49 numbers, okay? So that's not the probability of 1 ticket. 1 ticket means that we have a 1 in 13,983,816 chance of winning. 1 in 13,983,816 chance of winning. Now guys, if you want to know what that is in probability, hit 1, the divide button, and then type in 13,983,816, and you will get a decimal answer, and that'll tell you what your percentage is, or your relative percentages, okay? Not your relative frequency. All right, you don't have a very good chance of winning that lotto. I can tell you that. Now, combining these, just so we can see the difference of the two. And this is the final example. Here's your question. A corporation needs a president, a CEO, and a COO. CEO and a COO and a president, they're almost the same thing, but they just have slightly different functions, okay? They need those 3 to be selected from 8 members. It also needs a planning committee of 3 people where the president, CEO, and COO can be part of that committee as well. So they can be used in both of them. But we're going to have to solve these separately, okay? How many ways, the first question is, how many ways can we choose the officers? So we want 3 officers, president, CEO, and COO. Okay? And we want to know how many different ways we can choose them from those 8 members. So this is a permutation because order matters. You have 3 people. If you choose the president is the president. He's first place. You can think of it that way. The CEO is second place and the COO is third place. You can think of it that way. Okay? Order matters. So for my permutation, there are 8 people we can choose from. We want 3 of them. So this becomes 8 factorial over 8 minus 3, which is 5 factorial. 8 factorial over 5 factorial. And that answer gives me 336. There are 336 different ways that you could choose 3 people out of 8 people to be your president, CEO, and COO. Now, in contrast, we need a planning committee that also uses 3 people, and the CEO, president, and them can all be used. So there are 8 people still, okay, that we can select 3 for our committee. Now, our committee order doesn't matter. Anyone could be in the committee, doesn't matter. So this is a combination. So my combination is also 8 people with 3, and we would have 8 factorial over 8 minus 3, which is 5 factorial. And since it's a combination, we need 3 factorial again. When we solve that, you don't have to carry 8 down past 6, so 8 times 7 times 6 over 3 times 2, right? Because 3 factorial is 3 times 2. 2 reduces 6 down to 3, and 3 can reduce 3 down to 1, so really I'm doing 8 times 7, which is 57 ways in which you can, or 56 ways in which you can select 3 members out of 8. Now, do you guys see the difference between permutation and combination with the same numbers? It's quite a difference, okay? But anyway, that's how combinations and permutations work.